is the gas handling system and the high voltage drivers. This laser produced 10 microjoules per pulse at a repetition rate of up to 12 hertz. Average power is 0.15 milliwatts. In 2015, we demonstrated an even more compact version. All the pulse power is contained in this tank. Here is the laser head where the argon-filled capillary sits, and this is the vacuum manifold connected to the experiment. This newer version of the 46.9 nanometer laser produces 5 times more energy per pulse, 50 microjoules per pulse, and is commercially available through EUV lasers. To reach shorter wavelengths, it is necessary to rapidly heat the plasmas using an ultra-short pulse. So we use a scheme, as schematically shown here, in which the output from a shear pulse amplification laser system is focused to a line to create a plasma. And hundreds of nanoseconds afterwards, a short pulse excites the plasma to realize lasing at a shorter wavelength. This type of a scheme is equivalent, is electron impact excitation, is exactly the same process that occurs in an argon laser. So in order to achieve lasing at shorter extreme ultraviolet wavelength, we also have developed at Colorado State University that shear pulse amplification lasers at 1.03 microns that have achieved record 1 joule, 1 kilohertz, 1 kilowatt average power operation, and a petawatt class laser shear pulse amplification titanium sapphire system that produces 0.85 petawatts at repetition rates of up to 3.3 hertz. So using the optical lasers, Jorge Roca and his team have demonstrated a number of lasing transitions in nickel-like ions, for example, molybdenum at 18.9 nanometers, silver at 13.9 nanometers. And recently, they have reached zinc 6.1 and lasing at 6.1 and 6.6 nanometer in terbium. We use the output of the extreme ultraviolet lasers for nanophotonics applications. So we exploit the nanometer wavelength for microscopy, nanoablation, and nanomachining. And this is because the critical dimensions in an optical system scale with the wavelength of illumination. We use the high spatial and temporal coherence and high brightness to implement coherent lithographies, and we exploit the fact that the high energy photons can ionize any atoms or molecules, and that the absorption depth of the EUV light in most materials is a few nanometers, combined with the high spatial lateral resolution to demonstrate analytical nanoprobes. We have demonstrated microscopes using different extreme ultraviolet wavelengths operating at 46.9, 13.9, and 13.2 nanometers. This microscope can image nanostructures at resolutions that approximately wavelength resolution. And we can, because they offer high energy per pulse, we can image in single shot, and this in fact is a single shot image of 50 nanometers carbon nanotubes. So because the energy per pulse is very large, we can do single shot imaging. So actually exploiting, taking single shot images of an oscillating nanotip, we were able to construct this nano movie that depicts the motion of the tip. And we used this capability to actually probe magnetic interactions at the of this nanoscale tip that was magnetized at resonance. So when we place the tip on top of a permalloy strip, the stray fields actually change the amplitude of the oscillation of the tip. And this is what you can see here. This is the reconstruction of the motion of the tip when when the tip does not experience any force, and whenever it experiences a force, the amplitude of the oscillation changes by 40 nanometers. And these oscillations can be modeled as is shown here. Now at 13.2 nanometer wavelength, we implemented a microscope that is suited for EUV lithography mass inspection. So the constraints in these microscopes were that the illumination had to match the illumination conditions of the mask in a stepper. So to do this, we designed the microscope to use a condenser sun plate as well as an off-axis sun plate as an objective and to form the image on a EUV sensitive CCD. In this experiment, the laser was operated at 5 Hertz, and the average power was of the order of 2 microwatts. Using this microscope, we obtain very high resolution images. The spatial resolution is 55 nanometers half pitch of real EUV lithography mask. And from these images, we were able to obtain characteristic parameters that are used to determine the quality of the mask, such as the line edge roughness. So what is unique about these metrology tools is that it allows one to test the quality of the mask independently of resist response. There is no need to test the quality of the mask on the stepper tool. So next, I am going to describe the implementation of chemical imaging by extreme ultraviolet mass spectrometry. This is the very first laser ablation technique that reaches this nanometer scale resolution in 3D. So the concept of the method is schematically shown here. We take the output of the EUV laser, in this case, the 46.9 nanometer laser, and focus it with the sun plate onto the sample. To ablate the sample, then we extract the ions that are created in the laser created plasma, because there is an electrostatic system that is schematically shown here by this grid, and the sample that is set, the voltage at the sample that is set at typically is approximately 6 kilovolts. Once the ions are out of the field region, then their kinetic energy makes them travel to the microchannel plate. And so we measure the time of arrival, and then we calibrate to obtain the ratio of the mass over the charge. For each ablated spot, we get a spectra that looks like this, where we identified the content, the chemical content, by looking at characteristic peaks in the spectrum. We move the sample in 2 perpendicular directions across the focal spot, and we repeat the process to actually then be able to construct images, 2-dimensional images. And then if we move the sample along the axis of the laser, we get depth resolution. What you see here is that if we change the laser fluence, we can actually change the dimensions of the ablated spot. These are footprints of the laser beam in photoresist. And as you can see, we can actually ablate volumes that are very small, 2 attoliters. The smallest volume that we ablated and from which signal was obtained is 50 septoliters. This is the signal that we obtain in the amino acid alanine, where we can detect the intact parent ions. So in this system, we characterize the depth resolution and the lateral resolution. To characterize depth resolution, we use a sample that contains a layer of Nile red and alanine, and we consequently ablate it on the same spot on the sample until we reach the substrate, which is a glass slide covered with ITO. And we analyze the resulting single shot spectra for each ablation event, and we determine from there the content of alanine and in blue and of Nile red in red. And then to determine the depth resolution, we took the variation in the 20 to 80% change in the composition. And this distance is what gives us the depth resolution, which is 20 nanometers. We conducted a similar analysis now to determine the lateral resolution. And in this case, we use a sample that consists of a layer of resist in which a trench was defined by processing. We ablated in single shot throughout the sample. The total length here is approximately 15 microns, and the step size was 70 nanometers. And for each ablated spot, we got a spectrum, we analyzed and plotted the intensity of characteristic peaks in the resist as a function of position. So these are the type of images that we obtain. This image area corresponds to this rectangle shown here. And then we analyze the image to obtain the average profile. And from the average profile, again, we calculated the 80 to 20% change in intensity or in composition in this case, and determined that the lateral resolution is approximately 75 nanometers, which is 1 pixel. So exploiting the nanometer depth and nanometer depth resolution, and also tens of nanometers lateral resolution, we image in 3 dimensions the composition of a single bacterium. And these, what you see here, are isolines that of 2 significant lipid fragments that we observed in the spectra at 70.1 m/c and at 81.1 m/c. The voxel size was 0.3 by 0.3 by 0.08 microns cubed. We used the 3D imaging capabilities of the extreme ultraviolet time of flight mass spectrometry imaging system to also plot isotopic content. And to do that, we used a sample consisting of 2 oxide particles, micron-sized oxide particles that were consecutively ablated to obtain maps of the isotopic maps, as I show here. This map uses a pixel size of 300 nanometers. Here, what I show are equivalent maps of this region identified by the red square, in which the pixel that was analyzed using a pixel size of 50 nanometers. And as expected, we can see in the enriched sample the uranium-235, but we don't see it in the natural particle. So this is another example of the capabilities of the EUV time of flight mass spectrometry instrument. To implement coherent lithography, we exploit the short wavelength and the high spatial and temporal coherence of the EUV lasers. So these experiments were conducted using the 46.9 nanometer laser. And in this case, we are using, we demonstrated a technique that is called Talbot lithography. and that the Talbot effect was demonstrated in 1870, and essentially what it is a diffractive technique in which that shows that if we illuminate a mask containing periodic patterns with a coherent beam, then at certain distance from the mask that are called the Talbot distance, and that are defined in this way, where P is the period of the pattern in the object, and lambda is the wavelength illumination, then at certain distance from the object, an image is formed that is a one-to-one replica of the object. So if we now put here a wafer that is covered with resist, then we can capture this intensity pattern into the resist, and then when developed, obtain patterns like I show here in this photograph. So what is unique to this technique is that it's non-contact, lensless lithography. The exposures are very short, approximately 20 to 50 laser shots, and it is possible to print patterns over areas that are 0.5 by 0.5 square millimeters defect-free. This methodology has been pioneered by my colleague Mario Marconi and his group. So the defect-free capabilities of these coherent printing technologies are shown here. What you see here is the Talbot mask that we use that has defects. We use this mask to print on resist the pattern, and what you can see is that these defects do not appear in the print, neither when we transfer the print to gold. And the reason is that if you think about it, each of these cells is actually printed by due to the diffraction effect, is printed by the superposition from the diffractive beams from each of these cells within the mask. And so, in other words, the defects are smeared out. Now, this printed method is amenable to all the same capabilities and tricks that one uses in standard lithography. So Mario Marconi and his group demonstrated that it is possible to do double exposure to reduce feature size, and also a stitching of the patterns to print over larger areas. And doing this, they printed 40 nanometer lines with 110 nanometer line spaces over a millimeter square areas. They also demonstrated that it is possible to use, to do Talbot lithography using 18 nanometer wavelength laser output from extreme ultraviolet laser that operated at 100 hertz. And it took only 1 minute exposure to print a pattern over an area of 0.5 millimeters square. Now, if we combine with double exposure and stitching, we can essentially be able to print potentially 10 nanometer lines over very large areas, which is unique to this coherent printing with extreme ultraviolet lasers. So I have shown you all of the possibilities in terms of applications that are made possible by these bright sources of extreme ultraviolet laser light. And as I mentioned, the fact that these lasers are compact, they're tabletop, and are now commercially available, makes it possible for any researcher to implement these nanophotonics applications in a laboratory setting. So with that, I would like to thank you for your attention. And I would also like to thank my collaborators at Colorado State University and at the Center of X-ray Optics, who provided the sun plates for these experiments, and at the Lebedev Physical Institute that developed the Schwarzschild objective that we used in the microscopes. Thank you again for the opportunity to present our work.
Many thanks to Professor Carmen Menoni. Any questions? you have any questions to discuss with Carmen Menoni? Okay. Professor, I have one question. Because the reason you have development of EUV laser is extremely short wavelengths. So do you think it's possible or not to use the EUV laser to realize even higher resolution in the near future? For example, use some technologies just like STAT, which won the Nobel Prize in chemistry in 2014.
Technologies like or principles like STAT relied on fluorescence, and fluorescence is very weak at extreme ultraviolet wavelength. So I would say that it would be very difficult. However, there are imaging analysis schemes and other methodologies, for example, lithography, which may allow for higher resolution.
Oh, thank you. Thank you very much. Because of the time, and let's give a big hand to Professor and Carmen Menoni. Thank you.
Thank you. Thank you for the opportunity.